Now it is given as per as example point of view. We will start from the example number 1. In example number 1, it is given that a structured steel rod has a radius of 10 millimeter. So we are given a radius of a rod that is 10 millimeter. That means it is about 10 into 10 to the power minus 3 meter, that is 10 raised to minus 2 meter, and a length of 1 meter. So length is given as 1 meter of this rod. 100 kilonewton force stretches it along its length. So we are provided force, that is 100 kilonewton, that is 100 into 10 raised to 3 newton or 10 raised to 5 newton along its length. So calculate first stress. So first of all we are asked to find out stress. So stress, that is sigma, is given by force over area. So we can say that is sigma is force over area. We are given a force that is 100 kilonewton. So 100 into 10 raised to 3 over area, that is pi r square. Obviously pi is 3.14 and r is determined by 10 raised to minus 2 meter. So we can say that sigma is equals to 10 raised to 5 over 3.14 into 10 raised to minus 2 whole square. So this comes out to be about 3.18 into 10 to the power 8 Newton per meter square. So that is the stress that we have determined. Now second, they have asked elongation. So elongation is on the basis of that increment in the length. For that we can apply the equation of Young modulus, that to find out the elongation we know that the actual equation, that is Young modulus, is given by stress upon strain. Now stress, that is we have already determined, that can be written as F over A, and elongation is nothing but delta L over L. So now when we combine this, we can say that Young modulus Y is equals to F over A upon delta L over L, and therefore we can say that this delta L to be as F over A upon Y into L. So we have already determined the F over A, that is a stress, that is 3.18 into 10 raised to 8. L, that is length given as a 1 meter, upon the Young modulus. So the Young modulus is provided 2 into 10 raised to 11 Newton per meter square. So it is 2 into 10 raised to minus 11 Newton per plus 11 Newton per meter square, and therefore this comes out to be about 1.59 into 10 raised to minus 3 meter, or we can say that it is 1.59 millimeter. So after this much force, the elongation produced is about 1.59 millimeter. Now we also have to find out the stress and strain. So now we have calculated stress, now we can calculate the strain. So the question number C, that is strain is given by delta L over L. We have find out here delta L. So this would be, that is 1.59 into 10 raised to minus 3 divided by 1. So this comes out to be 1.59 into 10 raised to minus 3. But as it is in a fractional form, we can convert it into percentage mode. So if we convert it into percentage, so in percentage mode, we can say that it will be 1.59 into 10 raised to minus 1 percentage, that is about 0.159 percentage, or it can be written as 0.16 percentage. So the elongation, or after elongation, we can say that overall strain produced here is about 0.16 percentage. So this is your example number 1. Now we move further towards example number 2. So now what is there given in example number 2? That is also a straightforward example, but very good and IMP question. We are given that a copper wire of length 2.2 meter. So length is given 2.2 meter. A copper wire of length 2.2 meter and a steel wire of length 1.6 meter. So here we can say that length of copper is 2.2 and length of steel is 1.6 meter. Both of diameter 3 millimeter. So diameter for both are given 3 millimeter. That is 3 into 10 raised to minus 3 meter. So that is given 3 millimeter are connected end to end when stretched by a load. The net elongation is found to be 0.70 millimeter. So here they have given that the net elongation is provided. So obtain the load applied. Now the copper and steel wire are under the tensile stress because they have the same tension equal to their weight and the same area of cross section A. So from the equation, that is of the Young modulus, we can have stress is equals to strain into Young modulus. So we can say therefore that stress is equals to strain into Young modulus. Now here Young modulus of copper and steel, that is to be determined. So we can say here that sigma is nothing but W by A, that is equal for both. But elongation of copper, we can say that is delta LC over L, that is length of copper, into Young modulus of copper. In the same manner, for steel it is delta L of steel upon original length, that is LC L steel into Young modulus of steel. So we can say that from the Young modulus value and the given length, we can have the elongation of both the material. So for elongation of both the material, that means we can say delta LC upon delta LS. Delta LC upon delta LS is equals to Young modulus of steel upon Young modulus of copper and into original length of copper upon original length of steel. So when we put this equation in a required equation by given value of LC, that is 2.2 meter, and LS as a 1.6, while YC, that is a Young modulus of copper, is 1.1 into 10 raised to 11 Newton per meter square, and Young modulus of steel is 2 into 10 raised to 11 Newton per meter square, we have some condition, that is when we put the values of this value in above equation, we can have the solution of the equation, that is when we put different values as given, that is Young modulus of steel is 2 into 10 raised to 11 Newton per meter square upon Young modulus of copper, that is 1.1 into 10 raised to 11 Newton per meter square into length of copper is given, that is 2.2 meter, so it is 2.2 meter, and the value, that is length of steel, is 1.6 meter. So when we take the ratio of these, it comes to be about 2.5. Here it is unitless because it is of the same type of condition. Now the total elongation is given. So it is given that total elongation is 70 millimeter. So 0.70 millimeter. So now we can say that total elongation, as it is given in the textbook, is 0.70 millimeter. So we can say that delta L copper plus delta L steel is equals to 0.70 into 10 raised to minus 3. Now when we simplify it, this equation, it is clear that if we divide them in a term of delta L upon delta LS, so LC upon LS, we will have the condition of like delta LC upon delta LS. So if we divide whole equation with delta LS, we can have the value here. Delta LC upon LS is 2.5. This will be 1 is equals to 0.70 into 10 raised to minus 3 over delta LS. So if we want to find out delta LS, we can say therefore delta LS is equals to 0.70 into 10 raised to minus 3 upon 3.5. So if we put the values, that 0.7 divided by 3.5, it comes out to be 0.2. So it comes out to be 0.2 into 10 raised to minus 3 meter, or we can say that it is 0.2 millimeter. So now we can say that therefore This is your delta ls, that is elongation or the length increment in a steel. So for delta L copper, we can say that it is 0.7 minus 0.2 into 10 raised to minus 3 meter. So this will be 0.5 millimeter, as it will be delta LC. So it comes out to be like this, and therefore we can say that the total load applied, here we have to find out the load applied. From any of these value we can say, or we can determine that total load applied therefore is W is equals to A into Young modulus of copper into length increment in copper upon original length of copper. So by applying this equation we can have the value that is about 1.8 into 10 to the power 2 Newton. So this comes out to be the answer of the example number 4, and we will try to solve the example. So in example number 4, it is given that a square lead slab of side 50 centimeter. So it is a slab of 50 centimeter and thickness 10 centimeter is subject to a shearing force on the narrow face of it of about 9 into 10 raised to 4 Newton. The lower edge is reverted to the floor. So how much will be upper edge be displaced? So here lead slab is fixed and the force is applied parallel to the narrow face. So now it is very clear. If we consider the slab, this is suppose one base on which the slab is kept. We can consider that slab like a condition in a way that we can assume over here. This is the slab arrangement. Now we consider, suppose this is to be the level in which we consider. So let us draw again with little bit more proper figure. Let us consider this is one surface on which there is a slab. So this is one surface or a table like surface where we have kept the slab. So we can say that the slab is lying in this manner for the condition. So it is like this, like this, like this, like this. So this is the arrangement of slab. Now we can consider that in this arrangement of slab it comes under the shearing stress, and we can say that on the narrow path of it the force is applied. So due to this we can consider here that some shearing stress will be there to change its position in this direction. So let us consider it will move little bit like this, like this. This is the stress and the strain part. So here we can say that this is the actual elongation or the displacement take place in the object like this. This is the displacement takes place. Now regarding this, the angle will made here this is about a 50 centimeter side from this to this, and at the same time we are given a narrow 10 centimeter portion of a thickness. So this is about 10 centimeter. Now we are asked to find out this displacement. So we have to find out the value of this or this region. So here what we will do, here the question is actually simple, that first we apply the area on which this force is applied. So area is, that is length into thickness, so that is 50 centimeter into 10 centimeter, that is about 500 centimeter square. But in meter square, if we want to convert it, we can say that this is 0.05 meter square, as 1 centimeter is 10 raised to minus 2 meter. So therefore the stress applied, that we want to find out the stress applied over here, we can say that the stress applied is that sigma is force over area. So force upon area, and they have already given that force is 9 into 10 raised to 4. So that is 9 into 10 raised to 4 over 0.05. So it would be ultimately, so that would be about 180 or 1.80 into 10 raised to 6. So it would be, comes out be 1.80 into 10 to the power 6. So now this is the value of the stress applied on it. Now we know that shearing strain is equals to delta x upon L, and therefore it is equals to stress upon, that is total, the value of the condition, or we can say that it is called G. So here for the given condition, from the information we can say that G is equals to that stress upon strain. So if we make strain or shearing strain as a subject, it can be written, that is F over A into delta L over L. So we are asked to find out the delta L, or here delta X, that we have to find out in the condition. So here that delta L can be determined using the equation, that is that we can say, therefore delta L comes out to be F over A into L upon G, and if we take the table into the use, this comes out to be 1.6 into 10 raised to minus 4 meter, that is about 0.16 millimeter. So here we can find out that the displacement would be find out using this formula. Now after that we will apply another equation, another example, that is example number 5. So for that example number 5, what is the information provided here? That the average depth of Indian Ocean is about 3000 meter. So they have given the depth or normal height of Indian Ocean, that is about 3000 meter. So it is about 3 kilometer. Calculate the fractional compression, that is delta V over V, of water at the bottom of the ocean. So here we have to find out delta V over V. Given that bulk modulus of water, so we are provided the bulk modulus of water B as 2.2 into 10 raised to 9 Newton per meter square, and G, that is to be taken as 10 meter per second square. So from this equation we can have equation, that is bulk modulus is equals to that force over area upon strain. So that can be written as stress over strain, but here it is about volume. So epsilon is equals to sigma over bulk modulus. Now we can say this stress will be here pressure. So we can say pressure over bulk modulus, and for given condition and information we have the value, that is epsilon is equals to pressure is nothing but here rho g h over given bulk modulus. So for water, rho is 1000 kilogram per meter cube, g is to be taken as a 10, and h is given as 3000 meter. So we can put 10 to the power 3 into 10 into 3000 meter over bulk modulus, that is given 2.2 into 10 raised to 9. So 2.2 into 10 raised to 9. So this comes out to be about 1.36 into 10 to the power minus 2. But when it is converted into percentage, so again in percentage when we convert it, it will be equals to 1.36 percentage. So the ratio of delta V over V, or we can say that here that is a strain, that comes out to be 1.36 percentage from the top of the sea level. So this is your example.